In this video, we're going to take a closer look at the structural differences and similarities amongst these membrane lipids here. So in order to do that, there's going to be some things that are common and some things that are not. So let's talk about kind of the general thing that's going on here is when you look at, let's say, the phospholipids and the glycolipids here, you can see that we have all the same colors, right? You see the pink or peach color, some yellow, and some blue. And so those are going to have some general names to it. When you're looking at the pink glycerol right there, so the pink part or the peach part is going to be called the backbone. And from looking at these three types of membrane lipids, you can see that in phospholipids you have a glycerol, but then the backbone could be changed to a sphingosine. You can see all these different so there's just like for our examples here, there's two backbones here. And then you can see in yellow we have those fatty acids. And within the fatty acids, there can be variability in what type of fatty acid that you're using. When you come here to the archaeal lipids, you just have a carbon chain right here. It's not a fatty acid, but it kind of resembles a fatty acid. But it's just a long carbon chain. And these right here are significantly longer than the fatty acids in the glycolipids and the phospholipids. So we have fatty acid chains, or when you come to the archaeal, it's not fatty acids, but it is just a long carbon chain. And so you can change, so there's going to be diversity in the lipids based off of what type of fatty acids you have. And then, so we have the backbone, the fatty acids or the carbon chains, and then you have what's called the head group. And the head group is shown in blue. Now in the glycerophospholipids, you see the blue right here. We call these phospholipids because we're going to have a phosphate group. And that phosphate for all phospholipids is going to stay there. But the variability in phospholipids comes with this right here. I'm pointing to an alcohol, but that alcohol could be changed to other types of groups, which you will see shortly. And then you see with the phospholipids, but they're phosphosphingolipids, the phosphate group right here is going to remain constant, but then this piece right here, that can be variable, or maybe I'll draw it like that. So the head group in the phospholipids, there's kind of like two parts to the head group. There's the phosphate group, and then something attached to that phosphate group. And that something is variable, and that's going to give us diversity amongst the phospholipids. But when you look at the glycolipids, the head group in blue is a sugar. And then when you go to the archaeolipids, you can see that now it's kind of looking a little different here. We have glycerol right there, and that's not going to be considered a backbone. That's going to be a head group. And we have some phosphates here. So these lipids over here, they're a little different, okay? But those are the three big groups in lipids that we're going to take a look at. And as we adjust and change those up, we're going to get a variety of lipids. So the first thing that we can talk about here is focusing our attention on the glycerol phospholipids and looking at the glycerol group. Okay. So the glycerol backbone right here, here we have the glycerol 3-phosphate shown there. And make sure that when you look at this, you see here, so what does glycerol look like? So let's draw glycerol and make sure we see where all the changes are coming from. So glycerol would simply just be this guy right here. It would be that. There we go. So there's glycerol right there. Now when you take, and we know this is L-glycerol because the OH right here is on the left side when you look at the Fisher projection. Now what's interesting about glycerol is that for most of, so in the phospholipids category right here, the glycerol backbone is going to be L-glycerol. Okay. But then there can be archaeal ether lipids right here where they can change the glycerol backbone to D-glycerol. And so L versus D can give you some variety. But when we're taking a look at the phospholipids here and the glycolipids here, those are generally, the backbone is going to be L-glycerol. Whereas when you look at archaeal ether lipids, the glycerol backbone can be both L or D. So that's what you see here in the name, your L-glycerol 3-phosphate. And so there's the numbering scheme there. But why? Let's take a look at this right here. So this is another name for it. That's another name for our L-glycerol 3-phosphate. Why is it, what is that SN right there? Okay, the SN, that SN stands for stereospecific. Can I write it down here? Another way to designate the configuration of the glycerol backbone in lipids is to use this thing called stereospecific number. And a stereospecific number is a concept that by definition, okay, the carbon 1 right here in the glycerol, number 1 is going to be designated carbon 1 if that is the pro-S configuration. Now, a pro-S configuration, in organic chemistry, we have seen the configuration of S and R. We're familiar with that. But now we have this thing pro-S and pro-R. I'll talk about what that is in a second. But by definition, when you look at the glycerol backbone, why is this one right here, this carbon, why is that carbon 1? Because that's the pro-S arm. Let me explain. When you take a look at glycerol, it is an achiral molecule. There's no stereocenters. However, the moment you stick something onto this piece right here or that piece, either one, it's going to become a chiral molecule. So glycerol is a achiral molecule, but it can also be termed, hey, it's a prochiral molecule because if you attach something to it, it's going to be chiral. So if we look at an example here, how do I know this is the pro-S arm? Because if I erase that hydrogen right there, and I attach a different group, and by attaching that group, that's going to make this carbon the higher priority when we figure out if the stereocenter is R or S. So we've attached something to this carbon to give it a higher priority. So when we take a look at this stereocenter here, we do what we've done in normal organic chemistry class, prioritize the groups that's attached to it. So that's 1, 2, 3, and 4. And we ignore the 4 and we trace it, right? 1, 2, 3. So we're going in the clockwise direction, which makes it R. But the lowest priority group is a wedge, so we have to reverse that. So by changing this alcohol and making this carbon right here a higher priority, it makes this now is a stereocenter, and it is a S stereocenter. So this right here is the pro-S arm. And so right there, that's the pro-S arm saying, hey, if we make that a higher priority group by attaching something to it, that will give this stereocenter the S configuration. So you can see that the opposite is going to be the true if you change this. If you change that hydrogen right there to some, let's say, R group here, give back the hydrogen there. Now when you try to figure out what's the configuration of the stereocenter, 1, 2, 3, and that's going to make that stereocenter now an R stereocenter. So this right here, that piece would be considered the pro-R arm. And so when you see this name right here, saying, hey, we have the stereospecific number of glycerol 3-phosphate, that's telling us, hey, by definition, we said that carbon 1 is going to be the carbon with the pro-S arm. So that's going to be carbon 1, carbon 2, carbon 3. And so that's the way that we number the glycerol backbone, is based off of the stereospecific number. Okay. Now, if we go to the next slide here, let's take a look at our glycerol backbone. How would we number that guy? That'd be 1, 2, and 3. And from there, you could figure out what is the configuration of that stereocenter now, based off of how things are attached there. But now, let's take a look here. What we see for the glycerol phospholipids is that at carbon 1, we have a unsaturated, At carbon 1, we have a fatty acid that is saturated. Whereas at carbon 2, we have a fatty acid that is unsaturated. And that's just a key feature about these phospholipids, is that that's how it is. It's not swapped. When we go into nature and look at all the different cells and the cell types, and we look at their lipids in their membranes, this is what we see. That for the phospholipids, we have the unsaturated at the position 2. That's a key thing to remember. Now, as I said already, we can change these fatty acids up. And how the fatty acid looks is going to depend on the cell type and where that cell's found. Okay, so there's a lot of variety. Not every single cell in this universe has the same type of lipids. Okay. Another key feature that you need to remember. What type of linkage do we have here? How is the fatty acid linked to the backbone, a ester linkage. So we have ester linkages in our glycerol phospholipids. Another key a structural element that you need to remember. Okay, now let's just take a look at, remember the phosphate piece right there? In the very first slide that we looked at today, that was blue. But now we're going to focus our attention on the variability part. And that's what you see here. So when X in that previous slide is an H, then we have the phosphatidic acid. All right? And that is the name of the glycerol phospholipid. So we have all these different types of head groups right here. Here you see we're attaching a sugar. A very prominent one that we're going to talk about are these guys right here. And even this one. So there's that in itself, just the head group, changing it up a little bit is going to give us a different variety of the lipids. I am not expecting you guys to remember all these head groups and remembering the names. I do expect you to understand the general structure of a lipid, and everything else that I've said based off this. The ester linkage is important to remember, where they're linked up, carbons 1 and carbons 2, and all that I've already said. But you don't need to memorize all these structures. Okay. Okay, so now the PowerPoint's just going through why are these particular glycophospholipids so important. Oh, it's not glycerol phospholipids so important. And you can read up on that in your textbook. I'm not going to talk about that here. All right. So let's take a look at the sphingolipids. Here, we're changing the backbone. And the backbone in the sphingolipids is a phingosine. And you can see the structure right here. And when you zoom in and really take a look at it, it almost, this part right here, almost looks like glycerol. But we've put in a nitrogen atom in there, and we're forming a carbon-carbon bond right here. So it's different. But you could possibly see a little bit of glycerol design in that. Okay. And so what is different between a sphingolipid and a phospholipid? Well, one thing that should jump right out at you is that we have what type of linkage? What linkage right there is connecting the fatty acid to the backbone? That is an amide bond. So we have an amide bond right here that links the fatty acid to the backbone. Okay. And then this long carbon chain right here kind of looks like a fatty acid, but it's not, because it is part of the backbone. So with the sphingolipids, the backbone has a really long alkyl carbon chain, whereas in the other lipids that we just looked at, it's just the glycerol backbone. Kind of unique structure there. So we have one fatty acid in the sphingolipids joined by a amide bond. Now, as with the glycerol phospholipids, we can change the head group as well. Or we saw that we could change the head group, and so same thing with the sphingolipids. We can change that head group. Okay. and get a variety of different types of sphingolipids. As we go through the PowerPoint slide, you can see that it's going to talk about where can you find these sphingolipids, what are some pretty prominent ones. And you'll learn more about that as you read the textbook. I'm not going to talk about that here. So that gives us some examples of where to find them. Here's some more cool information right here. Okay. So sphingolipids are really important for determining the blood group that you have. Okay. Are you type O, type B, type A? It has to do with the sphingolipids that are in your blood cells. Kind of cool stuff. But the last class of lipids that I want to talk about are the archaeal lipids here. But we call it an ether lipid. Why? Well, we have not fatty acids. Okay. So I challenge you guys to, why is that in yellow? Why is that not a fatty acid? Okay. So go back to the other structures and pay attention to what makes it a fatty acid and not. But here we have just a long carbon chain right here. And what's interesting is that it's sandwiched between two backbones, two glycerol backbones right there. But how are those carbon chains, those yellow carbon chains, linked to the backbones right there? That is an ether linkage. And you can see also right there, that's an ether linkage as well. Now, why is this so significant? Because some of these archaeal lipids, like this one right here, are found in species that live in very intense environments. Crazy pH levels, high temperatures. And so these cells need to have a very strong cell membrane to live in such a drastic environment. So if you compare, let's say, a phospholipid to these ether lipids right here, which one's going to be a stronger lipid? Which one's going to be able to handle these extreme conditions? Clearly this one, because I just told you that. But chemically, why? Well, these have an ether linkage, and the phospholipids have what? An ester linkage. So an ester linkage in those extreme conditions would just fall apart. The fatty acids could fall off. Whereas if it's an ether linkage, it doesn't fall off and it's much more stable. So that's a cool feature that we see in creatures that live in extreme environments. The lipids in their cell membranes can look a little bit different. And it boils down to that ether linkage. Another interesting fact here is when we look at phospholipids or the sphingolipids, what do we have here? We have a head group, right? And then two fatty acids. And then they just associate with one another. Those should all be the same size. I'm not the best artist here. But we're going to make ourselves a membrane, a cell membrane like that, right? And so in that cell membrane, we have a bilayer. We have this top leaflet and a bottom leaflet. And that's what makes the outer layer of our cells. That's the membrane. Well, with archaeal ether lipids right here, look at what happens here. It is simply, make it a little bit longer here. So this piece right here, that's going to be that guy right there. And then this one right there is going to be this piece right there. And so some species don't have a bilayer. They just have a monolayer that creates their membrane, which is unique and really interesting. Okay, so I'm hoping that you guys are taking good notes on the key chemical structures that I've talked about, their key features, and what makes them unique and what gives them their properties here. This will be a good place to stop. As always, if you have any questions or concerns, please reach out. I'm more than happy to help.